Speaker for today is going to be Dhruv Batra. Dhruv is a research scientist at Facebook AI Research. He's my close colleague. He's also an associate professor at Georgia Tech. His research interest lies in the intersection of machine learning, computer vision, and AI. He's a recipient of several awards, including Presidential Early Career in 2000, Career Award for Scientists in Engineering 2019, and NSF Career Award for 2014, and several best papers. This is going to be a recorded talk named From Disembodied to Embodied Multimodal Learning.
Hi, everyone. My name is Dhruv Batra. I am a research scientist at Facebook AI Research and a faculty member at Georgia Tech. And I want to talk to you today about grounded language understanding. Let's begin by noting that in our research community and broadly, there seems to be a paradigm shift happening from disembodied AI systems towards embodied AI systems. And by that, what I mean is, on disembodied AI, static data sets studying supervised machine learning problems on large collections of images, videos, text, speech signals. And by embodied AI systems, I mean agents acting in environments. These could be physical agents like robots taking actions in the world, talking to humans in natural language, like the example illustrated here with a robot being asked by a human, is there smoke in any room around you? The robot replying yes in one room, go there and look for people. So there's egocentric perception, grounded natural language, question answering, and a dialogue. To virtual assistants sitting on smart glasses, taking virtual actions, but still talking to humans about egocentric perspective. And in this case, the body is not the agent, but the body is a human. Where did I leave my keys? On your coffee table. And if there's an AR device, show me the recipe for making guacamole, and so on. I think there is a core commonality here of embodied AI. It brings with it certain challenges like egocentric vision. In standard data sets curated from the web, images and videos are already pre-selected by whoever snapped that moment in time. When you have agents acting in environments, they capture visual content from an egocentric perspective. It is noisy, there is motion blur, and even those low-level problems aside, these look very different. There is no moment in time that has been curated. This is both a challenge and an opportunity. It is an opportunity because now we're in the active perception land. It means that there are no bad views because the agent can just move around and capture an object from another viewpoint. And the agent controls the incoming data distribution. One challenge that does exist in this scenario is sparse rewards. When you operate in the standard supervised learning setting, you make a prediction and you immediately get dense learning signals. This was right, this was wrong, this was right, this was wrong. In the kinds of tasks that we will be studying in embodied AI, it is going to be a long sequence of actions that typically in the end we know whether we succeeded or not. We will often set up dense rewards, but this is a fairly different paradigm where you may not immediately get feedback. And then of course there is the language understanding component of being able to ground natural language into the surroundings of an agent. So, this is an entire space that is almost being created as a community. I encourage everyone to look at the Embodied AI workshop that was held at CVPR 20. There was a lot of content there that was captured. And in particular, I strongly encourage checking out these two talks by Alison Gopnik and Linda Smith, who make arguments from a cognitive science and developmental psychology perspective for why, if we want to build AI systems, looking at how children acquire knowledge and skills might be a highly valuable avenue to pursue, and what embodied AI systems can learn from those perspectives. Okay, so what I want to do today is talk to you about these three things. The two first ones being papers, and one being, I think, a challenge that might be relevant to this audience. The first thing that I want to talk about is this line of work on vision and language navigation with image text pairs. And it's with this wonderful set of collaborators, some of whom who have moved on from Georgia Tech to a number of other locations. But these are the people who are really responsible for making this happen. So the problem I want to study is instruction-guided visual navigation. There is an agent, and it's spawned in an environment and given an instruction like take a left, go down the hallway, turn into the bedroom on the left, stop at the foot of the bed. So this is an instruction that the agent has to execute in an indoor environment. And this is what it might look like from in the agent's perspective. This is a slightly different instruction. Walk through the bedroom, go out the door into the hallway, walk down the hall along the banister rail through the open door, continue into the bedroom with the round mirror on the wall and the butterfly sculpture. Let's see how the agent proceeds. It's navigating from first-person view. This is a panoramic image that it observes at every step. We can see in the bottom left progress as the agent is making. This map is not available to the agent. This is just for visualization. And we notice that these are the objects that we're supposed to pass. Here's the banister rail. Here's the round mirror. And here's the butterfly sculpture where the instruction said to stop. And as soon as we see this example, it becomes clear that there is a language grounding problem here. The instructions are mentioning not just actions, but objects, certain fairly specific objects. The instructions are mentioning a banister rail, they're mentioning a round mirror, they're mentioning a butterfly sculpture. And this problem of, is this a banister rail? Iddentifying these things. This is, of course, the classical symbol grounding problem. It has been with us for decades. This idea that symbols must be grounded into sensory motor perceptual signals in order for us to be able to talk about the entities that we observe in our environment. And this is a challenging problem also from a AI machine learning perspective, because we are always going to have a long tail of visual concepts. So in the room-to-room data set collected by Anderson et al., I am plotting a distribution of the tokens or the objects that are mentioned in these instructions. And we can notice that there are some things like rooms, stairs, door, right, left. Some words are very frequent. So rooms are talked about always, stairs are talked about frequently, but then there's this long tail of words, entities, actions that are mentioned that are very rare in the data set. So at the very end of this distribution, there is a long set of words that are only mentioned once. You see one instruction containing a word like marshmallow, and it might say, stop at the marshmallow. And if because there's only one, it is present either in train or test. If it is present in test, you've never seen that word before. But even if you have seen that once before, this is a challenging problem. We're going to have to develop systems that are able to stop when they see something completely novel. And the way we're going to attack this problem is we're going to step back and say, this is not a new problem. People in, disembodied or internet dataset regimes have looked at this problem significantly. There have been developments of, large-scale models for encouraging language grounding and for datasets for studying these problems. The key question that we are going to be asking is, can we transfer visual groundings from disembodied but highly prevalent web data to sparse embodied tasks where there is not a lot of data? So do I really need to learn what a marshmallow is as I'm learning to navigate? Probably not. I may have seen pictures of a marshmallow on the web, and why don't I learn what this token means from other data sources and apply it here? So that's the research question. It is not an obvious yes to this question. The answer to this question is not an obvious yes, for reasons I will mention soon. The data set that we're going to be looking at is something called the Conceptual Captions data set. It's a wonderful resource released by these folks listed down here, which contains images and captions for those images. they are automatically, at least partially automatically curated. So there is some noise in the data set, but it is extremely large. There are 3.3 million pairs in this data set. And we're going to use this data set to try and ask the question, if we use this data set, so first, how can we use it? And two, does it help in vision and language navigation? So the question is, can you take this picture containing this scene and blue sofa in the living room, the caption, and can you use it to learn what a sofa looks like and then follow instructions? Turn left, go out the patio, walk behind the sofa, stop at the sink. So this is the formal task setting here. There are two immediate problems you run into. One is that conceptual captions is a static image data set. It contains images. And the task that we're concerned with is a dynamic task. It contains image sequences. The images themselves are panoramas in our task and not just narrow field of view images. The second bigger problem here is that the images look very different. When someone puts pictures of sofas online, they tend to be curated from a particular iconic view meant to highlight certain aspects of the layout. But when an agent is navigating in an environment, the sofa is incidental. You just see it at the side of the field of view, and the images therefore look very different. And this is true for other concepts like kitchens as well. Doors are particularly illustrated because nobody takes a picture. If there is a category called door, then likely the door was closed. If an agent was navigating and it saw a door, likely the door was open, because if it was closed, these data sets, these simulators do not yet have the capability of having the agent open the door itself. So the door will always be open. So there are challenges. How are we going to overcome these challenges? Well, so first on the modeling side, what we're going to do is we're going to develop models that try to preserve as much as possible from the disembodied literature to the embodied literature. And so we're going to step back, and I'm briefly going to talk about this paper that we presented with these sort of collaborators at NeurIPS last year called ViLBERT. It's a vision and language BERT style model. And then I'm going to talk about how to adapt this for VLN-BERT. And so here's a brief summary of ViLBERT. It is a two-stream transformer model where there is one stream meant for the image and one stream meant for the sentence, or because this was studied for image captioning. So this picture and the man shopping for fruits in a store. The language stream is fairly straightforward. The input to that is tokens, the start token and each of the tokens in the words in the sentence. There is cross attention between these two streams. For the vision stream, we're going to run a pre-trained detector, a fast RCNN model, to extract regions in these images, and the regions and the features corresponding to those regions are going to be the tokens for the visual stream. So that's the architecture. And what we're going to use this for, and how we're going to pre-train this, is similar to masked language model pre-training. So we're going to perform masking on the language side by hiding certain tokens. We're going to mask on the vision side by hiding certain regions. On the language side, we're going to be predicting tokens from vocabulary. On the vision side, we're going to be predicting features at those regions. And so this can be done in a completely self-supervised manner once you have images and captions. You do not need grounding supervision. You do not need to know where the man is located. We do not need those annotations. And finally, this can then be, after this pre-training, can be fine-tuned for tasks like, does this caption correspond to this picture? So you can fine-tune it for that. So that was ViLBERT. We are going to use this architecture for the vision and language task and create an architecture for VLN-BERT. And we're going to try and make intentionally as few changes as possible so that we can reuse a majority of the parameters in this architecture. So what we're going to do is, moving from images and captions, we're moving to a sequence of panoramas to a sequence of sentences. Dealing with the language side is straightforward. The words, again, become our tokens here. And instead of a single sentence, we have multiple sentences, but handling that is trivial. Dealing with the vision side is slightly trickier in that you don't have a single image, you have a sequence of images. It is also easily addressable by creating multiple regions from these images. I encourage you to check out the paper for those details. And it's basically that you have a sequence of regions corresponding to viewpoints along a particular pathway. So we're going to give this a trajectory, and we're going to give this a sentence, and we're going to train this for predicting whether this trajectory corresponding to a sequence of panoramas and this sentence are aligned or not. Is this a good alignment? Is this a good trajectory corresponding to the sentence? And we can also fine-tune this for producing how good is that alignment, and then, of course, use this for ranking different trajectories. And that's exactly what we're going to do. So given a trajectory of paths, we're going to be able to rank them based on this score or energy function. Okay, there are going to be 3 stages of pre-training in this architecture. So there is the language-only pre-training, where all you see are sentences. So there is no visual stream. There is just a language stream of ViLBERT, which is just BERT. With that is going to be pre-trained on Wikipedia and book corpus. There is the image caption pair, so the second stage of pre-training, and that's going to be on conceptual captions. And finally, the third stage of pre-training, or training, if you will, is going to be on the room-to-room data set for vision and language navigation, which is on path instruction pairs, where we produce a sequence of a set of paths from an existing architecture, because we're going to be in the setting where we are re-ranking paths, and we're going to show positive and negative examples of path instruction pairs, and we're going to train on that. The first stage obviously is initialized from BERT. The second stage is initialized from ViLBERT. And so this is establishing how much of that pre-training helps. We will do ablations of this. And the third stage is, of course, on the room-to-room data set. Okay, so let's see how well this works. If you don't do any of the pre-training that I mentioned and directly jump to the room-to-room data set, the VLN-BERT architecture gets you at 30.52% success rate. For that many episodes, you are able to reach a thresholded distance of the final target location. This is not bad, it's not trivial, but this is fairly far away from where the state of the art is. If you do language only pre-training on the Wikipedia captions, on the Wikipedia dataset, we achieve 45% success rate. So clearly, just simply understanding sentences, even though they're coming from the web, they seem to have nothing to do with indoor navigation, is quite useful. We see a 15% boost there. If we perform language plus visual grounding, which is what ViLBERT does, or language plus action grounding, where if we jump from stage 1 to stage 3 directly, in both of those cases, we see an additional 5% improvement over just language only pre-training. So both those data sets and both those stages of pre-training are individually helping over language only training. And of course, the full curriculum of first doing language training, then language and visual grounding on conceptual captions, and then the training on R2R gets us to 59.26, which is 9% better than just a not doing doing 2 of the 3 stages of training, and of course 29% or nearly 30% better than no pre-training at all. So this number right here establishes the value of both pre-training on language alone and pre-training on conceptual captions, so visual grounding. So we see a significant boost here in how well we can follow these instructions. And notice these are identical architectures. This is the exact same architecture. So this is quantitatively telling us the value of the pre-training done on the web data. So clearly, this helps a lot. And in terms of comparisons to state of the art, this is the leaderboard for this task on Eval AI, which is evaluation platform, challenge hosting and evaluation leaderboard platform built by Devi Parikh and my labs. This is a open source project, but also publicly available for people to use. VLN in particular is one of the more active challenges. VLN-BERT is located pretty high up on this leaderboard. There was, we are getting 73% success. Human performance is 86. We're only slightly behind what is the #1 entry. And this is a fairly active leaderboard with lots and lots of submissions that happen regularly on this task. So this is fairly competitive performance. And we can actually see quite intuitive qualitative results. So we can see, for example, that for this instruction, turn right, then turn left, turn right into the room, then wait near the antelope head. The ground truth path is shown in orange. The agent traversed path is shown in blue. Yes, there are errors. It is not perfect, but it reaches the right location. So it deviates a little bit. More importantly, if we implement gradient-based visualization techniques to know which regions the model is attending to the most, we actually do find that at the last node in this sequence, the model does attend to this region, which actually does contain the antelope head. So there is no supervision for any of this. We've never actually shown it ground truth boxes corresponding to an antelope head, neither in the R2R dataset nor in the conceptual captions pre-training stage. But it's nice to see that that emerges from this pre-training, from this large-scale pre-training. Here's a failure case where the navigation fails. Walk out of the bathroom, pass the sink in the shower, walk down the hallway, turn into the bedroom with hanging curtains. We can see that the path selected by our model is this blue path, and it is incorrect. It follows it for a while, but it is incorrect because it does not end up at the same stopping criteria. But if we look at for this token hanging curtains, where does the model look? It actually does identify a region where it actually does identify hanging curtains. It just is not the last node in this path. And this right here is actually illustrating a limitation of our approach, in that we do not actually impose that the regions, we do not put this as a restriction that the regions attended to by tokens must be in a particular order, so that by the time you have reached the last token in the language, you should also be looking at a region which corresponds to a panorama taken at the last node in the trajectory. And that's certainly something that can be improved upon in this model. Okay, and here's a question that we had alluded to quantitatively, but now it's also good to look at qualitatively. Does pre-training improve visual grounding? And we know the performance improves, but turns out that visual grounding also improves. So here is VLN-BERT with conceptual captions. This instruction was go through the door to the right of the door to the wine room. Turn right, go into the next door to the mini fridge. And we are looking for what regions are attended to for the mini fridge. When we choose a model VLN-BERT with conceptual captions pre-training, it actually does place highest attention mass on a region corresponding to the mini fridge. When we pick the identical model, so the architecture is the same, but simply drop the pre-training of the conceptual captions, no such mini fridge region is attended to. So we've, at least there's qualitative evidence to suggest that the improved performance may be coming from the improved visual grounding, which was one of our hypotheses that we wanted to test. Okay, here are the pointers for the various papers and things I mentioned. And with that, I'll stop, and thank you again for having me. The only message I'll leave you with is I think we should all seriously consider this transition that is happening and think about more assistive agents that can be trained to follow instructions and other things in these simulated environments, and consider other aspects of embodied AI. Thank you.
Thank you so much, Dhruv, for preparing this awesome recorded video. I would like to ask Dhruv to also join us for the Q&A. And I see on this stage, Dhruv already has started answering several questions. I'm going to skip over those that Dhruv already answered and start with the ones that he has not yet. Let's see. So Aditya had a follow-up question. Dhruv, let me know if you answered that one, but somehow related to the above question, how often are trajectories compared to the query? Is it only at the start or at every move of the agent?
Sure. First of all, Albert, can you hear me all right?
Yep, you're all
awesome.
Good.
Okay. Yeah. So I was getting to that in the text. I think one thing that perhaps may not be immediately clear, and I should have done a better job at this, is that what we're doing is we're re-ranking trajectories in this paper. So there is a list of action trajectories that are generated from another model, and what we're doing is we're sort of comparing that the images corresponding to that trajectory to the language, and we're re-ranking them to pick one. So this happens all at once. If you are coming from a control theory background, you would call this open loop planning as opposed to closed loop planning and closed loop control. We have work in progress where we can also do closed loop control, so that the sentence comes in entirely to you at once, but you don't have to make a full commitment about the trajectory. You can take an action, see what image you see, and go from there. But that is not yet published work. We're still working on that.
Great. So Rami Iskander asking, how do you order the image regions in ViLBERT?
Yeah, so there was a related question asked earlier as well. So the image regions have no natural one-dimensional ordering. They do have spatial coordinates, which are useful. And so what we do is we have a raster scan sort of order, but it's really not the ordering that matters. It's the positional encoding of the center of the bounding boxes that give any notion of grounding and position in the image. But instead of raster scan, it could have been an arbitrary order, but it wouldn't have mattered because it's really the positional encodings that are doing the heavy lifting.
And a follow-up question by Rami again. Did you experiment with a hybrid model where image regions replace words? For example, replacing the word man by an image of a man.
Well, so to be clear, there are two branches, right? There's a language branch where there is language, and on the vision branch you actually have regions. And to be clear, the vision branch is doing what you're saying, that you just have image regions. You do not have any grounding. And so I suspect what you're suggesting is that even on the language branch side, instead of actually the word just feed in a canonical image corresponding to that, we haven't done that. I suspect it's no easier to compare a canonical image of a man with what you see in this image, which may not be the same. But this is just a conjecture at this point. But the answer is no, we haven't tried this.
Thank you. Let me go through Kshitij Jain. If I pronounce the name incorrectly, please excuse me. What is the no pre-training model?
Yeah, so it's the same model, except the only thing different is that we train our parameters from scratch on the room-to-room dataset for the VLN task. So there is just absolutely no pre-training on conceptual captions dataset. And the point of comparison to that model is to show how much of the gains are coming due to the architectural choices and how much of the gains are coming due to pre-training.
Got it. Let me see. So Mustafa Mirshikari asking, how do you think it would be possible to ensure alignment between the text and video sequence? And specifically, if the agent does not look at the right object at the right time, the navigation might make big accumulative errors.
Yeah, I think that's a good question, and the observation is absolutely correct. In any of these sequential decision-making tasks, mistakes made early on have cascading effects, and so it is important to get those early ones correct. I think, how do you ensure proper alignment? So this is a question that people struggle with, not just in the embodied setting, but in the disembodied setting as well, whether you're doing image captioning or image grounded dialogue or AR grounded dialogue or VLN, you struggle with this problem. There are a few different ways, right? I mean, you could take the large scale data approach where you say that, look, I'm never going to have supervision, but I will have enough loosely paired data, like the one conceptual captions, where if I see enough of it, I'll figure out what word is referring to what part of the image. And the answer there is to just get more data. It's going to be noisy, but that's one sort of theme of approaches. And the other can be that I'm going to start getting more and more involved supervision. I will never be able to scale up my data set, but I will have a fairly aligned data set. And there has been recent work from Google. There's been 2 recent papers, one for image captioning. I'm blanking on the exact phrase that they used, but they asked Mechanical Turk users to use a mouse pointer, and as they were describing the image, to move the mouse pointer on the region that they were describing. So if they say there's a man standing next to a car, the mouse pointer is tracking. When they say man in speech, the mouse pointer is on the man, and when they say car, it is on the car. So you get these loose groundings of image captions and images. Peter Anderson and Jason Baldridge at Google have extended that to the VLN task as well. So you can try to get grounding supervision, and that's one way of overcoming this.
I think maybe like even the closed loop can also help over there. So as you're navigating, you can course correct. I'm gonna thank you so much, Dhruv, for joining us. I'm gonna close this session. There are some other questions. If Dhruv, you would kindly also answer the rest of the folks over there. We're gonna move to the last invited talk for this session.